Okay, recording has started, so good afternoon, everyone. Let me show you all of the resources which I'm going to give you in terms of how to prepare for the final exam. So first and foremost, I'm going to do a practice exam like usual. So I'll post the practice exam sometime soon, and then I'll also post a video solution guide, like I've done with all the other exams, to the practice exam on YouTube. So you can try the final exam under exam conditions, and then check yourself and check your work against the solution guide and see how well you did. So that'll be the practice exam. I'm also going to post bullet points like I did for the last exam of things that you should know how to do for the final exam. So I'm still working on putting that together. And in addition to that, I've also posted this document to the Blackboard. Wait, maybe it's easier for me to just open it. Where did I put that? I put this document on the Blackboard with information on where the problems are going to come from. Okay, so your final exam is going to be, what, 7 pages? So it's 70 points total. So in other words, like 7 10-point questions. So the first exam was 6, the second exam was 5. This one will be a little bit longer than both of them, but not by much. And you got 2.5 hours, which is double time. So double time to do a slightly longer exam. And I'm going to do 1 page covering chapter 1 and 2, 1 page covering chapter 3, 2 pages from chapter 4, and then 3 pages from chapter 5 and 6. So like I have already said, there's going to be a recency bias in the sense that there's going to be more content on this integration stuff than there will be on the derivative stuff. But you'll still need to know how to do chapter 4. There's 2 pages, 20 points of the exam comes from that. So you'll still need to know how to find the derivative of functions, find the local max, local min, find the global max, global min, and do optimization. Okay, so that's still going to be on the final exam. And chapter 3 was just how to do derivatives, so basic derivative calculations, like quotient rule, product rule, chain rule, all of those. And then chapter 1 and 2 was like average rate of change, exponential functions, half-life and doubling time, and those sorts of things that we did way back in January or February. Okay, so that's the breakdown, and it's on Blackboard too, so you can click that if you want to take a look at it. Any questions about that? Okay. So in addition to that, I'm going to post the bullet points of things you should know how to do, and I'm going to post the practice exam, and I'm going to post the solution video guide to the practice exam. And I will also hold a 2-hour review at some point next week, in addition to the 1 hour and 15-minute review we're going to have in class on Thursday this week. Homework-wise, I posted a homework a while ago, which is going to be due this Friday. It's on 5.5 and 6.2, and it's 28 questions, but most of them are short. Like the last 15 or 20 of them are all just like basic antiderivatives. They shouldn't take you too long. But if you struggle to meet that deadline, then just email me. I'll extend it for you. It's fine. And I'm going to post another homework on 6.3, which is optional. Okay, so I'm not going to take the homework on 6.3 for a grade, because I don't want you to feel stressed out during dead week or finals week or whatever week it is. So that homework is going to be optional, but I recommend that you do it because 6.3 is going to be fair game for the final exam. In fact, there will be content on the final exam coming from 6.3. So I recommend that you try those problems just so that you're aware of that material. Okay, I left this up here, how to check your final exam grade, how to check what grade you need on the final exam to get the grade that you want in the class. And I'm also doing this quiz retake thing. So if you want to retake one of your quizzes except for quiz 5, then you can do so before class, basically on Thursday this week. So come early, 15 minutes early on Thursday if you want to retake one of your quizzes. So I recommend that you retake the one that you got the lowest score on, because if you can increase your grade, your quiz grades, you can increase your final grade by like as much as 6%. So please, please, please make use of that, because that is basically how I plan to sort of massage our grade distribution in lieu of a curve. I'll still use a curve if it is absolutely necessary, but based on what I'm seeing of the current grades and the impact that I anticipate the drops of the quizzes and the drops of the homeworks and the retake of one quiz of your choosing to have on the grade distribution, I think we're going to be in a good place. Yeah.
Are like the grades that are on Blackboard for like the quizzes and stuff, do those, like the total like running average of say like the quiz or the homework, are those including the drops, or would we have to like calculate
the quiz average? There's a column that says quiz average with drop. That is your quiz average with drop. Your homework average is, first of all, not up to date, and second of all, doesn't include the drops. So your homework average should probably be a little higher than what it looks like in Blackboard. Any other questions? Yeah.
Are there drops included in homework as well?
Yeah, the two lowest homework assignments will be dropped, and the two lowest quiz scores will be dropped. And I will only include quiz 5 in your average if it helps you. All right, any other questions? Okay, then, yeah, all the quizzes, by the way, are on Blackboard, so please study the quiz that you want to retake. And you can just basically study your mistakes, see what you did wrong. Aha, I see I'm supposed to do it this way instead. Then you come in and you just ace it because you already know what questions are on the quiz, right? So you can take a look at those on Blackboard and study them. Guarantee yourself a 10 out of 10 on one of these quizzes. All right. Are there any other administrative questions before we start material for today? Also, the last quiz is going to be today at the end of class. Pretty sure that's today. Yeah, that's today. I better set an alarm for myself so I remember to stop pontificating. Okay, so we got 50 minutes to finish up basically the rest of Calculus 1. So there's some stuff which inevitably I'm just not going to be able to get to. I had hoped to do some U substitution, but I think to learn U substitution properly, I would need to use about 2 days, and I have 0 days left. So we're just going to finish up section 6.2 and do section 6.3, which gives you the gist of what all of this integration stuff has been for. So let's just recall what we learned last time, which is the fundamental theorem of calculus. So that has a very big and important sounding name. So what did it mean? It said that if we have a function and we know that function's derivative is continuous, then what is true? The integral from a to b of f prime of x dx is equal to what? It's equal to the total change of f over that interval, okay? So this is really fascinating. What it says is that if we have a function and we look at the difference between that function and its derivative, okay? So this is the derivative and this is the function. Then the difference in height from 0 to 3 of this function is equal to the area under the curve of the derivative from 0 to 3. So this area, which is in this triangle, is the same as this height, which is viewed as the function. And that's really great because there are all sorts of circumstances where we want to find out what is the area under the curve when the curve looks all kinds of crazy. Finding the area under a curve which is all kind of crazy is hard. But if we were to be able to know what is a function whose derivative is that function, then all we would need to do is check the difference in height from 0 to 3. That's easy to do. We just take one number minus another number. It's easy to do one number minus another number. It's hard to find the area of this shape. Okay? So this is the idea behind the fundamental theorem of calculus. And you know, it doesn't sound that useful yet, because the way we've stated it is, well, if we know what the original function is, then the integral of its derivative is going to be what we get when we plug into the original function. But what we're going to learn today is, what if we just start out with the derivative and we want to know what is the integral of that function? But I don't know what is the parent function. Well, that's where antiderivatives come in. I can find out what is the antiderivative and then plug into it, and that's going to give me what I want. So that's where we're going. But to get there, we started off last time by talking about antiderivatives. So we wanted to come up with functions. If we know that what the derivative of that function is, how can we come up with what the original function was, right? Before we took its derivative. And the way we did that was, well, first we just saw this example of how to do it with a constant, right? So we know if the function's derivative is a constant, then the original function had to have been a linear function with slope 3. But one interesting thing that we noticed was there's actually multiple functions whose derivative is 3. We could do the derivative of 3x, or we could do the derivative of 3x plus 1, or we could do the derivative of 3x plus pi, plus 1,000, plus 1 million, 100 million. Who cares? We can add whatever we want on the end of this function, and because we're taking its derivative, it's just going to go away. And we're going to be left with 3. So this left us in a bit of a quandary to say, okay, well, which one is the antiderivative? And the answer is, well, there's not really a the antiderivative for a function. There are many antiderivatives for the function. Okay, so that's why we use this word n antiderivative. I don't say the antiderivative because there's multiple. So n antiderivative, capital F of x of little f of x, is just any function such that if I take its derivative, I get little f. So for example, if little f of x is 1 over x, then an antiderivative could be ln of x, or ln of x plus 1, or ln of x plus anything we want. Okay, it's just a function whose derivative is what we started with. Any questions so far? Okay, so for the rest of this section is about how do we find various different antiderivatives. So that's what we're going to learn. It's kind of like the reverse of all our derivative rules, right? We learned how to do the derivative of all sorts of different types of functions, right? Now we're going to learn how to do the antiderivative of a few functions. Not as many as we did with derivatives. But okay, so we were doing this in the middle of this exercise here, where we were trying to determine which of the given choices is an antiderivative of the given function. And to determine whether capital F of x is an antiderivative of little f of x, all we had to do was take its derivative and see if we got f. Okay, just check if it's an antiderivative, then the derivative of the antiderivative should be what we started with, right? So that's how you can check antiderivatives. And now we're going to learn some, now we're going to learn some, should I start with, okay, I should start with this. I'm gonna skip the rules really quickly and go down to this box on definite and indefinite integrals. So I want to draw a distinction between the notation of what we call a definite integral and what we call an indefinite integral. So this one is definite. Okay, when I say definite, I'm referring to the fact that this integral is taken over an interval from a to b. Okay? Now, if I do the integral of a function from a to b, then this is defined to be the area under the curve. From a to b, which is a number. Okay? There's some area under the curve. Well, actually, I should say area. I should modify this. I should say area between f of x and x-axis, which is above the x-axis. And I'm going to take that number and I'm going to subtract the area beneath the x-axis. And whatever those numbers are, I take them and I subtract them, and my end result is a number. So anytime I see this integral from a to b of f of x dx, I know that it's just standing in the place of what is in reality just a number. Okay, so what's different about an indefinite integral? Well, when I use this notation, like so, you'll notice the big difference between these notations is one of them I have bounds and the other one I don't. Okay, so this is the notation that I use to refer to. So the indefinite integral refers to the collection or family of all antiderivatives of little f of x, i.e., this is the same thing as capital F of x plus c, where c is what we write to refer to the fact we can add any constant. Okay, so it's a little bit different. Indefinite integral, I get a family of functions. Definite integral, I get a number. So indefinite integral, what do I get? I get whatever is any antiderivative plus any number. Okay? Plus any number. So this is a collection of all the numbers. So for example, if I were to do the integral of 1 over x dx, then I would refer to the family of functions who have the form 1 over x plus c, not 1 over x, sorry, ln of absolute value of x plus c, where c is any number. Okay, so this is what I mean when I write the indefinite integral. I'm referring to the family, the collection of all antiderivatives. And the way I write down all antiderivatives is, well, every antiderivative will have the form of one of the antiderivatives plus a constant. Okay, so this is the big difference between definite and indefinite integrals. Okay, so now we're going to learn how to do some indefinite integrals, which again, they tell us what is the antiderivative of a function. Okay? So any questions on this definition / notation before we move on? Yeah.
So the integral of the indefinite form, will it always have the form capital F of x plus c?
Yes. So whatever little f of x is, capital F of x will just be an antiderivative of that. So for example, when I do the specific one for 1 over x, the capital F of x in this one is the ln of absolute value x. Okay, and then the plus c is just there to say that, well, yes, ln of x is an antiderivative, and I can get all of the other ones, I can capture all of the other ones by just adding something to it. Could be I'm adding a negative number, right? I could be subtracting 2. Okay, so let's see how this works in reality. Okay, so we're going to learn 4 antiderivative rules. So these are going to be the functions which you are responsible to know how to find the antiderivative of. Okay, so the first one is easy. It's just a constant. Well, I need to think of a function whose derivative is a constant. What function am I thinking of? Yeah, a linear function. Any other specifications? Just any old linear function?
Has to be a linear function with, like, where one, part has a variable and the other is a constant itself, right? It can't just be one that just has a variable.
Okay, so is the integral of 2 dx, could I do 3x? Is 3x an antiderivative of 2? No, why not?
It has to be a 3.
Yeah, the 3 isn't right? The slope, that's what tells us how we get the derivative, right? The derivative of a linear function is the slope. So if I think of a function whose derivative is k, then it should be a linear function whose slope is k. And then, of course, I can add any constant that I want to that, and it's still an antiderivative. Okay, so for example, the integral of 2 dx would be 2x plus c, okay? So indefinite integral, I don't have bounds here. My answer should be a family of functions. It is the family of functions which are given by 2x and then adding any number that I want to that. Any questions on the first one? All right, let's try the second one. I have a function whose derivative is x to the power n. So what are going to be some features of a function whose derivative is x to the power n? It's going to be x to some other power, right? If I take x to some other power and I take its derivative, what happens to the power of that function? You subtract it by 1, right? So if I'm doing the opposite, what might I want to do? Add 1, right? So we might think, okay, maybe the antiderivative is x to the n plus 1, right? Let's think about that for a second. When we do the derivative of something like this, what do? We don't just subtract the power by 1. We also multiply times n plus 1, right? So if we were going to reverse this process of multiply by the old power and subtract the old power by 1, to reverse that, what we need to do is divide by the new power. Divide by the new power and add 1 to the power. Okay, so you see how if I were to take the derivative of a function which looks like this, I would get x to the n, right? Because what would happen if I did the derivative of this? I would take the n plus 1 down front. So it'd be n plus 1 times x to the n, and all still being divided by n plus 1. And then the n plus 1s would cancel, and I'd be left with just x to the n, right? Okay, so this is how I find the antiderivative of x to the n. And of course, I need to add c. So anytime I'm doing an indefinite integral, you should always have a plus c. Okay, because if I just write this part, then it looks like I'm saying that it's the unique antiderivative of this function. But we know that there's many antiderivatives of that function. So we want to talk about all of them. Okay, next one. What function has the derivative 1 over x? ln, right? So the antiderivative is actually ln of the absolute value of x. Okay, so small difference here. When we are doing the antiderivative here, because x is allowed to be negative in the original function, when we take its antiderivative, we need to avoid the possibility that we plug a negative number into a natural log, which is why we use the absolute values here. Okay, so it's log of absolute value of x plus c. All right, now how do I reverse an e to the kx derivative? What's the rule for doing the derivative of e to the kx? What do I do? Yeah, you take k times e to the kx, right? So basically I just leave it as it is and multiply by k, right? So what's the reverse of that process going to be? Yeah, leave it as it is and divide by k, right? So a function whose derivative is e to the kx would be something like e to the kx over k, right? Because I would do the derivative of this guy. This guy's just a constant, so he's going to hang out in the denominator. And the top, what I'm going to do is just do the derivative of e to the kx. So what would I get? I get k e to the kx divided by k, and the k's would cancel, and I'd be left with that function, which was our integrand. Okay, so 4 different ways which we can do antiderivatives here. So 2 rules that I want everyone to remember, which we've already discussed, really. Actually, we've only discussed this for definite integrals, but it's actually also true for indefinite integrals, is that if I do the indefinite integral of 2 functions being added together, okay, then I'm just going to get the integral of one plus the integral of the other, okay? i.e., I can treat this kind of like how I treat sums when I'm doing derivatives, okay? So if I were to do the integral of, say, 2x plus 3, okay, then this is the same as doing dx. This is the same as doing the integral of 2x dx plus the integral of 3 dx. Now, if I did each of these integrals on their own, I would get x squared for the first one. That's the function whose derivative is 2x plus c. And then I would get 3x plus c, right? And the way that we treat this plus c is the way that this line reads. Okay, I take x squared, and then I add any constant that I want to it, and then I add 3x, and then I add any constant to it that I want. And then whatever those constants are, I can just combine them into another constant. So I end up with just x squared plus 3x plus c. Okay, so this is how I do the antiderivative of a sum. I just take the antiderivative of each piece. Just like how when I'm doing derivatives of sums or differences, I just do the derivative of each piece that's being summed or subtracted. Okay, and likewise with a constant multiple, you can pull it out. Okay, so the integral of 2x, okay, is just the same as the dx is the same as the integral of 2 times the integral of x dx. Okay, so if you want to pull constants out front, that's also fine. Okay, so these are all of the rules which we are going to learn for doing integration. And from here, we're going to do a little bit of practice finding antiderivatives. Okay, we're going to do a little practice finding antiderivatives. And then we are going to see how antiderivatives fit into this fundamental theorem of calculus business. Yes?
For number 4, does that one have a plus c too, or is that different?
Oh, no, of course that is the same. I just forgot to write it
Okay.
because I'm also human. Okay, so e to the kx over k plus c. All right, so let's see some examples here. So for each of these, I'm going to do the first one, and then we're going to work in a group here. So the first one, what we want to do is find the integral of 2x dx. Okay, and then for the other ones, same deal. It'll be integral of 3x squared minus 3 dx equals question mark. And then same deal, integral and integral for the last two. But let's do the first one together really quickly. All I need to do is find a function whose derivative is 2x. Well, I can do this in 2 ways. I can just memorize the fact that I know that when I do the derivative of x squared, I get 2x, and then I can have that. Or what I can do is I can apply the x to the n rule. Here I can rewrite this as 2 times the integral of x to the 1 dx. Okay? And now I'm going to use the rule where n is 1. So I'm doing the integral of x to the 1. It says I should increase the power by 1 and divide by the new power, and then add c. So that's exactly what I'm going to do. I'm going to just leave that as 2 times x. I increase the power by 1, it becomes 2, and I divide by the new power, and that's 2, and then I add c. So I'm left with these 2's cancel, and I just get x squared plus c. Okay, so two different ways you can do it. If you can automatically see what the antiderivative is going to be, which you will be able to do after you have some practice under your belt, then you can do it that way. But you can always come back and rely on these 4 rules. Well, these 5 rules, I guess. 5.5 rules if you count the sum and constant multiple. Okay, so let's form groups and try to work on finding the most general antiderivative for each of B, C, and D together in our groups. And if you have any questions, just raise your hand and I'll come around to your group. Okay, I'm gonna zoom this out a little bit so that you can all see the rules. Can everyone still see what the problems are? Okay. That way we can keep the rules on the screen. You don't have them written down yet. Rule 5.5 or 6 or 5.5 says, right, is if I have a sum of two functions, then finding the antiderivative of their sum comes down to just finding the antiderivative of each, right? So,
Yeah, I went to see it. I got X cubed.
Derivative execute, right? We put that 3 down, we make power 1 less. So that's going to be that part, so we're going to get x cubed.
So I did 3.
How about the second part? What's the second part? X squared minus 3. But I'm not really sure what you do with the minus sign. Well,
It would be.
you want to preserve that minus sign, right? So you can either think of it as 3x squared minus 3x squared as 3x squared plus negative 3.
I think that's going to be the first one.
Right, but what's the antiderivative?
So just constantly just like that.
Yes, so yeah,
So it must be the minus
subtract
3
that
Always
because the 3 is being subtracted. And now we're nearly there. We just got one thing left to do. That's right. Let's see. Okay. And now for the second one, rule 4 is going to
I haven't gotten to the
rule 4 and rule 6. I think we're going to need to put that in.
Yeah, I mean, I don't know exactly how, but maybe that would make the most sense to me.
Anyone else have some questions?
You said you can.
What was your answer?
You said you pull out the first and like.
Well, I guess it's a matter of personal preference, right? So you could think about it in 2 ways. You could say to yourself, well, I know a function whose derivative is 3x squared. What is it? Yeah, next to the third, right? So you could just immediately go. Or you could pull the 3 out and then use this rule, right, which says xpn, well, we raise the power by 1, so it would become 3. So, okay, but the plus 1 needs to be on that power, right? You see how it's in the power? So this would become x cubed divided by 3. So, and the integral sign would go away, right? Because we've done the integration. You see what I mean? Yeah, so we get rid of that. So we found the expected in this function, which was x cubed, and you multiply it by 3 to get that out. Right? But really, actually, if you pull that 3 out, this 3 needs to come out.
So then that
It's like the whole thing. So I think this one happens to be All right, let's come back together as a group. So I saw some excellent work out there. Great job, everybody. So we're going to go through these together really quickly. So I saw some very different strategies being employed on this first one, and it comes down to a similar business as what I did here. Okay, so the question is, do I want to just look at 3x cubed and immediately think of a function whose derivative is 3x cubed, which is possible for this one just because this function's quite nice, or should I try to leave the 3 as a constant and try to do the antiderivative of x squared on its own? So two different ways we could do it. Let me show both ways. The first way is just to recognize that, well, the antiderivative of 3x squared, I actually know a function whose derivative is 3x squared. It's the function x cubed. And I know that just because I've done the derivative of x cubed 1 million times, right? So that's one way. And then for the minus 3, of course, its derivative is minus 3x, right? Antiderivative of any constant is just the linear function. And then, of course, I should add c. So that's the first way to do it. But let's say that you were stuck in a position where you saw 3x squared and you didn't immediately recognize that that was the derivative of a function which you know already. Well, let's use the rules which we learned. We know that the 3 is just going to hang out. And I know how to do the derivative of a function, the antiderivative of a function like x squared. What do I do with a function like x squared? I raise the power by 1, so it would become x cubed, and then I divide by the new power. Okay? Then I know how to treat negative 3 by the first rule, right? Integral of a constant is just that constant times x. So that's how I get minus 3x. And guess what? These two are the same, right? Because if I do 3 times x cubed and then divide by 3, those 3's are going to cancel, right? And I'm going to be left with this guy. Do you see what I mean? Okay, so 2 different ways we could do that one. We could use the rule if you want, or if you have done a lot of derivatives and you recognize, aha, that's the derivative of a function that I had done that derivative a million times, then you can just go ahead and move on. Okay, but it got a little more complicated with part B, right? Oh, I guess I went the wrong way. Okay, part B, we had to do the integral of 12e to the 6t plus 1. Which rules did we have to use to do part B? Yeah, we had to use the rule number 4, right? And rule number 1. Okay, so what I'm going to do is just do the integral of 12e to the 6t plus 1 dt. To do this, I'm going to do the first part first and then the second part second, and I'm going to add them. Okay, so for the first part, I'm going to leave the 12 alone. And now what I need to do is write down whatever the derivative, or not derivative, whatever the antiderivative of e to the 6t is. Which is what? What is the derivative of e to the 6t gonna, the antiderivative of e to the 6t gonna be?
E to the 6t over 6.
Yeah, just e to the 6t divided by 6. Okay, it's like the opposite of the chain rule here. Instead of multiplying times the derivative of that inner function, I'm dividing by the derivative of that inner function, because I'm reversing this process. Okay, now plus what? Plus t, just one t, right? And then plus c. And I'm done. Okay, so if you want to simplify this, it could be 2e to the 6t plus t plus c. Okay, how could I check my work if I did an antiderivative to see if I got it right? Yeah, you could do the derivative of your answer and see if you get back what you started with, right? Okay. How about square root t? This one was just a trick question, wasn't it? How do I think of square root t so I can do it? That's right, t to the 1/2. Same way I think of square root t when I'm doing derivatives. So I'm doing the integral of t to the 1/2 dt. So what should I do in this circumstance? Which rule applies? Rule number 2. Thanks, Gino. Okay, so we got rule number 2. So I know that I need to raise that power by 1 and divide by the new power. Well, that just means I do t to the 3/2, and I should divide by 3/2. So that means I get, and I add c, of course. So that means I get 2t to the 3/2 divided by 3, because dividing by 3/2 is the same as multiplying by 2/3. So I get 2t to the 3/2 divided by 3 plus c. Okay. Any questions on these 4 problems that we did for the group work? All right. Then we're going to learn the last thing we're going to, the second to last thing we're going to learn for today. Okay, so I said before, right, that an antiderivative is not necessarily unique, right? Antiderivative is not necessarily unique. So how could we potentially single out one specific function? Well, if I have a query which results in multiple answers, and I want to decide between the multiple answers, what I can do is ask for an additional assumption to be satisfied. Okay, for example, if I were to ask, who is the person in this room whose last name is Miller, right? I wouldn't be able to do it because there's a Mike Miller and there's a Ben Miller, right? But if I said, who is the person in the room whose last name is Miller and is wearing a hat, right? Then I can single out Ben. See what I mean? So that's going to be the idea with initial value problems. So if capital F of x is equal to the integral of little f of x dx, and we know capital F of c is equal to some number, then we can figure out the unique function capital F of x which satisfies both of these properties. So we say, okay, not only is f of x an antiderivative of little f, but we also know that what is the value of the function at one point. And that's going to nail down for us what the constant should be, okay, in the following way. So let me show you an example. So if we were to say no, that the derivative of our function is 2x plus 3x squared minus 7, and I also knew that when I plug in 1 I get 10, I can figure out what the constant is, because I know that capital F of x is going to be the integral of little f of x dx, which is going to be equal to x squared plus x cubed minus 7x. Okay, so that's 3 rules. I use the power rule twice and the constant rule once. Plus c, right? But furthermore, I know that capital F of 1 is what I get when I plug in 1, right? So that's 1 squared plus 1 cubed minus 7, and that's equal to 10. Minus 7 plus whatever the constant is, and that's all equal to 10. And now you can see how I can figure out what the actual constant is, right? I can just solve for it. I add 7 to the other side, that's 17. Subtract 2, that's 15. And that tells me c is going to be 15. And therefore, capital F of x is equal to the function x squared plus x cubed minus 7x plus 15. Okay? So, I say, if I just say my function's derivative is 2x plus 3x squared minus 7, you're not sure which one I'm talking about, because it could be x squared plus x cubed minus 7x plus 40. But if I say, no, not plus 40, it's the function such that if I plug in 1, I get 10. Then you can figure out what that additional constant is with that extra information, okay? So, antiderivatives are not unique unless I pair them with this extra information, which is called an initial condition or initial value, which is why we call these initial value problems. Okay, so I'll put some of those on the maybe on the 6.3 homework if you want to practice some of them. Any questions about that? Yeah.
So I'm kind of confused exactly how you got to, how you found out that 15 was the value of c.
Okay, so I know because capital F of x is an antiderivative of this guy, that it's going to look like x squared plus x cubed minus 7x plus c for some number c. And because I have f of 1 equals 10, I know that if I plug in 1 into this function, what do I get? I get 1 squared plus 1 cubed minus 7 plus c. And I know that should be equal to 10. So I have 1 plus 1 minus 7 plus c is equal to 10. So I add 7 to both sides. And then I minus 1 from both sides and minus 1 from both sides for the ones. So if I add 7 and subtract 2 to 10, then I get 15, right? So it's just a simplification from that step. But the key here is to find out what is the general form of f of x, then plug in 1 and set it equal to whatever the other side is, right? Or maybe it's f of 0 equals 10, or f of 1 million equals negative a million. Make sense? All right. Okay, so from here, I have to move on for the very last thing which we're going to learn today, to section 6.3, which is the culmination of everything that we've been doing so far, which is the fundamental theorem of calculus restated in a slightly different way. Okay. So here's how we're going to restate this. If capital F of x is any antiderivative of little f of x, then the integral from a to b, so this is a definite integral, we're going to get a number, of f of x dx is equal to capital F of b minus capital F of a. Okay, so why is this incredible? It's incredible because I can find the area underneath any curve by, as long as I can find an antiderivative, I just have to plug in b and a and subtract, and I'm done. Okay, so let me show you how fascinating that is. Okay, let me show you how fascinating that is. I'm going to start with problem B here. Well, if I can find a function, capital F of t, such that capital F prime of t is equal to 5 over t, then the integral from 1 to e of 5 over t dt is going to be equal to capital F of e minus capital F of 1. Okay, so as long as I can find a function whose derivative is 5 over t, right? So what function has the derivative 5 over t? Can we think of one? Close. 5 is going to hang out outside, and then we need a function whose derivative is 1 over t. It's going to be ln, right? So, by rules 4 and 5, no, not 4 and 5, I think it was 3 and 5 from the previous section, capital F of t will be 5 times ln of the absolute value of t. So this is a function such that if I take its derivative, I get 5 over t. And now I can determine that the integral from 1 to e of 5 over t dt is equal to 5 times ln of e minus 5 times ln of 1, or absolute value of 1, whatever, which is just 5 minus 0, which is 5. Okay, why is that incredible? That is incredible because what this thing represents is actually the area underneath a very weird looking curve. 5 over t looks like this. Okay, and you say, I'm going to start counting area at 1, and I'm going to stop counting area at e. And I'm going to check what is all of this area in here. What does it all add up to? 5. And I would be like, if I saw this for the first time, I'd be like, what? How is that area 5? How do you do that? Well, we just learned this really powerful technique that says whatever the function is, as long as you can find an antiderivative of that function, which we have just discussed how to do for a handful of functions, as long as I can find an antiderivative of that function, I just plug in e, and I plug in 1, and I subtract. Okay, so this is what, this is what Riemann and Lebesgue and all these famous mathematicians spent like centuries trying to understand how to do, is how do we find out what is the area under a weird looking curve like that? And the fact that it comes out that you can just find any antiderivative and plug in is like really astonishingly elegant of a result. Okay, but I'm done trying to convince you why this is cool. Let me show you a couple more examples. We're not going to break into groups because we're low on time. But let me show you a couple more examples real quick. All right, we want to do the integral from -1 to 1 of 2x squared minus x dx. Okay, well, I know by the fundamental theorem of calculus that this is going to be equal to, I just need to find n antiderivative of 2x squared minus x. And I know one such function would be the function, well, I raise the power by 1 and divide by the new power, so it becomes 2x cubed minus, 2x cubed over 3. And then I subtract x squared over 2. I raise the power by 1, divide by the new power. And then I'm going to draw this little bar here on the right-hand side, which signifies that I've already done the integration, and I just need to plug in -1 and 1. So all I'm going to do is plug in 1 first. I get 2/3 minus, when I plug in 1 for that, I get 1/2. So that's what I get when I plug in, this is f of 1, and then minus f of 0, which f of 0 is what I get when I plug in 0 into this function, which both of them will be 0. So in the end, I get 2/3 minus 1/2, or if you want, let's see, we could call that 4/6 minus 3/6, which is 1/6. So 1/6 is the area underneath the function, underneath the function 2x squared minus x from -1 to 1. So let me repeat the process one last time. We find an antiderivative of the function. Then we plug in 1, we plug in the top bound, and then we do a minus sign, and then we plug in the bottom bound. And that's it. So we can do that for any of the functions which we have learned how to find antiderivatives for. For example, for this one, its antiderivative would be 2e to the 0.5x divided by 0.5. And then what would I do? I would plug in 0 and 1 and subtract. For the next one, I need to find an antiderivative of 2t squared minus 5t plus 1. Well, it's just going to be 2t cubed over 3 minus 5t squared over 2 plus t. And then, what do? I plug in 0 and 2 and subtract. Question, Gino?
In the first example that you did, the lower bound was -1, we did at 0.
Oh, thanks. Yeah, sorry. This should have been a -1 here. -1. So here I should have put, something different. I should have put -2/3 minus 1/2. And then whatever you get when you subtract those things. Thanks for catching that. Yeah, I plugged in the wrong number. Okay, so that's it. That's our whole class. So I hope you enjoyed it. I hope you learned something. And we're going to do the quiz. So please put everything away except for a pencil. And if you want a calculator, but it won't help you. But if it makes you feel more secure, then you can put it on your desk. And if you're wearing like an Apple Watch or something like that, please take it off and put it in your bag and close your bags, please. So I'm going to distribute these quizzes. Please keep them face down on your desk until everyone has one. Okay, everybody has a quiz? All right, you may begin.